This is a tutorial on the digital filters that are used on the precision, low bandwidth Σ-Δ converters. For the tutorial I will use the AD7124, the AD717X and the AD719X families. The AD7124 are low noise, low power parts with an integrated feature set and multiple diagnostics. The AD717X are low noise, high speed parts, and the AD719X are low noise parts with an integrated PGA. The main purpose of the digital filter is to reject out-of-band noise. A Σ-Δ modulator performs noise shaping, so the noise in the band of interest is reduced and the noise is pushed to a higher out-of-band region. The digital filter will reject this out-of-band noise. On the three families that I have mentioned, we offer multiple filter options, and this offers flexibility. The filter type chosen does affect the RMS noise, the 50-60 Hz rejection, the settling time and the stop band attenuation. So we will see that trade-offs are needed between these four specifications. To review the filtering, I will use the online virtual eval tools. These tools are available at betatools.analog.com/virtualeval, and I will begin with the AD7124-8. All the Σ-Δ converters have sync filters, so even our older parts used sync 3 or sync 4 filters. Sync filters are chosen because they have low latency. This means that the settling time of a sync filter is lower than other digital filter types, for example an FIR filter. This is important in a multiplexed application where we want to optimize the throughput. Using a sync filter means that the conversion time for each channel is minimized compared to other filter types, and therefore the throughput is optimized. The AD7124 has a sync 3 or sync 4 filter. The AD719X family also offers a sync 3 or a sync 4 filter. And we will see later that the 717X family, along with the sync 3 filter, also have a sync 5 filter. So let's begin by comparing the filter profile of the sync 3 and the sync 4 filter. The AD7124 is set to its default output data rate of 6.25 samples per second. With the sync filter, notches are placed at the output data rate and multiples of the output data rate. And note the width of the notch for the sync 4 filter. In a system that's operated from the mains power supply, there will be interference at 50 Hz or 60 Hz, and the notches of the sync filter can be used to reject that 50 or 60 Hz interference. The other thing to note is the stop band attenuation. A sync 4 filter gives over 50 dB attenuation in the stop band. Let's compare this against the sync 3 filter. With the sync 3 filter, you can see that the notch locations have not changed, so they are still located at the output data rate and multiples of that frequency. However, the stop band attenuation has now degraded to 40 dB. Also, the notch is narrower with the sync 3 filter compared to the sync 4 filter. Also note that the roll-off is less steep with the sync 3 filter compared to a sync 4 filter. I mentioned previously that the notches can be used to reject 50 or 60 Hz. If I select an output data rate of 50 samples per second, this will place the notches at 50 Hz and multiples of 50 Hz. I still have the sync 3 filter selected, so you can see with this filter I am getting 95 dB rejection at 50 Hz. If I select the sync 4 filter, again I will get 50 Hz rejection, but now because of the wider notch I am getting 129 dB of rejection. Some people like to design systems that will reject both 50 and 60 Hz, so the system gives simultaneous 50 and 60 Hz rejection. To design this filter with a sync type filter, an output data rate of 10 samples per second could be used. However, this will lead to a longer settling time and a slower throughput. Another option is to use the Reject 60 function that is available on the AD7124. When the sync filter is programmed to have an output data rate of 50 samples per second, the Reject 60 function places a first-order sync notch at 60 Hz and multiples of 60 Hz. So with an output data rate of 50 samples per second, you can achieve simultaneous 50 and 60 Hz rejection. We are getting 82 dB rejection. If I now select the Sync 3 filter, again we achieve simultaneous 50 and 60 Hz rejection, but now we're achieving 66 dB, so we are getting less rejection at 50 and 60 Hz with the Sync 3 filter. Next, we will compare the timing of the Sync 3 and Sync 4 filter. We have the Sync 3 filter selected and the output data rate programmed to 50 samples per second. So with the single channel enabled, conversions are available at 1/50 or 20 milliseconds. You can see that the time for the very first conversion is longer. This would occur if, for example, the gain were changed or the configuration was changed. The very first conversion takes longer, and the time for that conversion is dependent on the sync order. Because we have a Sync 3 filter selected, the time for the first conversion is approximately 3/20 or 60 milliseconds. The actual time is slightly longer as the filter and modulator are reset before the ADC begins sampling the analog input. If we compare this against a Sync 4 filter, again the time for conversions is 1 over the output data rate, or 20 milliseconds in our case. However, the time for the very first conversion is now longer. The time for the first conversion is now 4/20 or 80 milliseconds, and again the time is slightly longer because the filter and modulator are reset before the analog input sampling begins. Next, let's look at noise performance. We have the Sync 4 filter selected and the output data rate is 50 samples per second. You can see that the RMS noise is 1.4 microvolts and the peak-to-peak resolution is 19.04 bits. If we compare this against the Sync 3 filter, so again the configuration is the same, you can see that the RMS noise is now 1.7 microvolts and the peak-to-peak resolution is 18.95 bits. So there is a slight degradation in noise performance for the Sync 3 filter, but it's not a significant difference. If we now pick a fast output data rate, we can then compare the Sync 3 and Sync 4 filter again. So I will choose the fastest output data rate, which is 2.4 kilosamples per second for the 7124 in the low power mode. You can see with the Sync 3 filter that the RMS noise is now 870 microvolts and the peak-to-peak resolution is 9.8 bits. Again, with the Sync 4 filter and the same configuration, you can see that the RMS noise is now 72 microvolts and the peak-to-peak resolution is 13.3 bits. So at the fast output data rates, the higher order sync filter is giving better performance. Generally, at low output data rates, the performance in terms of noise of the Sync 3 and Sync 4 filter is similar. However, at the fast output data rates, and this is the area where the noise floor is rising in the sigma delta modulator, the higher order sync filter rejects that noise better, resulting in better noise performance and better peak-to-peak resolution. Next, let's evaluate the performance when multiple analog input channels are enabled. I will enable 2 analog input channels and I will set the output data rate to 50 samples per second. All 3 families have a sequencer, so multiple channels can be enabled and the sequencer automatically converts on each of the enabled channels. Looking at the noise performance, you can see that the RMS noise and peak-to-peak resolution has not changed. Also, the filter profile has not changed. So noise performance, filter profile are not affected by the channel count. They are the same whether it's single channel or multi-channel. Note we programmed the part to have an output data rate of 50 samples per second, so you can see our notches are located at 50 samples per second. However, when we look at timing, you can see that conversions are no longer available at 1/50 or 20 milliseconds. You can see that the time for the very first conversion is the same for single or multi-channel. However, the time for subsequent conversions increases when multi-channels are enabled. Every time a channel is selected, the filter needs to settle, so the filter must be loaded with information that is relevant to the new analog input channel. For a Sync4 filter, this is approximately equal to 4 multiplied by the conversion time for a single channel, which is 20, and that equals 80 milliseconds. So the time for every conversion is approximately 80 milliseconds. Note that the output data rate no longer is 50 samples per second. It is reduced by a factor of 4 because we are using the Sync4 filter, so our output data rate is 12.4 samples per second now. Comparing this against a Sync3 filter, specifications such as noise and the filter profile are not affected by the multi-channel. They're the same as when a single channel was used. However, the timing again has been affected by the multi-channel operation. As with the Sync4 filter, you can see that the time for the very first conversion has not changed for multi-channel versus single channel. However, every conversion now needs the complete settling time of the filter, so each time an analog input channel is selected, the complete settling time must be allowed for that channel to generate a valid conversion. Because we're now using the Sync3 filter, that means that rather than getting conversions every 20 milliseconds, we are now getting conversions at 3 by 20 or 60 milliseconds approximately. To see the performance of a Sync5 filter, let's look at the AD7175-2. As I mentioned previously, the AD717X family have a Sync3 filter, but they also have a Sync5 plus Sync1 filter. On a part like the AD7175-2, when the fastest output data rate is used, a Sync5 only filter is used. So in this case, the fastest data rate is 250 kilosamples per second, and when this data rate is selected, you can see that a Sync5 only filter is selected. For other data rates, a Sync5 plus Sync1 filter is used. So looking at the Sync5 filter, we have an output data rate of 250 kilosamples per second. So note the notch locations are now at 250 kilohertz and multiples of that frequency. The stop band attenuation is greater than 60 dB. And also the roll-off is much steeper with this higher order filter. So comparing a Sync3, a Sync4 and a Sync5 filter, in terms of noise performance, all three filters give similar noise performance at low output data rates. However, at high output data rates, where the noise floor of the modulator is rising, the higher order sync filter gives best noise performance. In terms of throughput, the Sync3 or lower order sync filter is best, as it has minimum settling time compared to the Sync4 or Sync5 filter. In terms of filter profile, the higher order sync filter has best roll-off, best stop band attenuation, and the widest notches. So even with a Sync3, a Sync4 and a Sync5 filter, trade-offs are needed. If I select a slower output data rate and still use the Sync5 plus Sync1 option, a Sync5 plus Sync1 filter is now being used. This means that the Sync5 filter is still being used, but this is followed by a Sync1 filter. And a Sync1 filter is basically an averaging block. So following the sync filter, an averaging block is included. The different output data rates are implemented by varying the amount of averaging, and this is done automatically on the 7175 part. So on the AD717X parts, when an output data rate other than the fastest output data rate is selected, the Sync1 block is included. And this block, as I said, averages, the amount of averaging changing depending on the output data rate selected. The 7124 parts also include a Sync3, Sync4 plus Sync1 block, and the Sync1 block again is an averaging block. Averaging by 16 is performed in the full or mid power modes, and averaging by 8 is performed in the low power mode. These filters are known as fast filters on the 7124. The 719X also have similar fast filters, and on these parts the user can program the averaging to be 2, 8 or 16. The benefit of including a Sync1 block after a Sync3, Sync4 or Sync5 filter is that the settling time for every conversion is now similar. So remember, with the Sync3 filter, for example, the time for the very first conversion was different to the time for subsequent conversions, and also the time for those subsequent conversions depended on whether the part was operated in single channel mode or multi-channel mode. When the Sync1 block is included, the time is now similar for the very first conversion, for subsequent conversions, whether in single channel mode or multi-channel mode. So from a firmware point of view, a user does not have to concern themselves about varying settling times depending on the mode of operation. So let's look at the filter profile of the Sync5 plus Sync1 filter. I have the part programmed to have an output data rate of 50 Hz or 50 samples per second. So again, note that the notches are located at 50 Hz and multiples of 50 Hz. However, the roll-off is now less steep. So firstly, the stop and attenuation is now only about 13 dB. We do have notches at the output data rate and multiples of the data rate, but those notches are now narrower. So if I'm using that notch for rejection of a tone, I will get less rejection of that tone. With an output data rate of 50 samples per second, I can use the Sync5 plus Sync1 filter to reject 50 Hz tones. But note, I am only getting 33 dB rejection at 50 Hz. To achieve simultaneous 50 and 60 Hz rejection, I would need to use a slower output data rate. So if I program the part to have an output data rate of 10 samples per second, this will place a notch at 50 Hz and also a notch at 60 Hz. However, because the notches are narrower, I am not getting a lot of rejection at 50 Hz or at 60 Hz. So I am only getting about 33 dB rejection at 50 Hz and 35 dB rejection at 60 Hz. The key benefit of the Sync5 plus Sync1 filter is the similar settling time for every conversion, whether single channel or multi-channel. So I am not using extra time for latency or settling time because this is automatically built into the filter type. For good 50 and 60 Hz rejection in a reasonable settling time, the AD717X family have enhanced filters. These consist of FIR filters, so following the Sync5 filter, an FIR filter is included. The AD7124 also have these filters, but they are known as post filters or FIR filters. The benefits of these filters are that you get good 50 and 60 Hz rejection in a good settling time. The 717X family have 4 options, and these same 4 options are included on the AD7124. So let's pick an output data rate of 20 samples per second. Looking at the filter profile, you can see that we have a lot of notches, but there is a notch located at 50 Hz and a notch located at 60 Hz. So in terms of rejection, we are getting 86 dB rejection at 50 Hz and 90 dB rejection at 60 Hz. So we're getting very good 50 and 60 Hz rejection. Looking at the timing of the FIR filters or enhanced filters, you can see that the time for every conversion is similar, whether it's the first conversion or subsequent conversions. Also note, our output data rate is 20 samples per second. Our conversion time is very close to 1/20 or 50 milliseconds. If I now increase the channel count to 2 and again look at the timing, you can see that the timing is the same. So the time for the first conversion and the time for subsequent conversions again is very similar for the FIR filters. So this is really useful if you want to design a system where you want simultaneous 50 and 60 Hz rejection and you want the maximum throughput. With this filter type, we are getting very good 50 and 60 Hz rejection, but the settling time needed for every conversion is less than a standard Sync3, Sync4 or Sync5 filter. This allows you to design a multi-channel system that is very good simultaneous 50 and 60 Hz rejection, but the throughput time is minimized compared to a standard sync type filter. The last thing to consider is chopping. This is available on the AD719X family, and chopping is used to minimize offset and minimize offset drift. This feature is not available on the AD717X family or the AD7124 families, as these parts inherently have low offset and low offset drift. As I said, chopping is used to minimize offset and minimize offset drift. Chopping is implemented by swapping the analog input pins. So with the pins connected in one direction, a conversion is taken. The input pins are then swapped and another conversion is taken. Those two conversions are averaged, and this averaging, while minimizing offset and offset drift, it also affects the filter profile and the throughput or settling time. By default, the AD7193 is programmed to use the Sync 4 filter, an output data rate of 50 samples per second, and chopping is turned off. With the chopping enabled and using those other default settings, you can see that we are achieving deep notches at 50 Hz and multiples of 50 Hz. The chopping introduces extra notches, and these are useful because we can now achieve simultaneous 50 and 60 Hz rejection. With the sync filter placing a notch at 50 Hz, the chopping introduces a first order notch at 60 Hz, so we are achieving simultaneous 50 and 60 Hz rejection, and we are getting about 63 dB of rejection. Other things to note are that with chopping enabled, the stop band attenuation is now only about 5 dB. Also, the roll-off is less steep with chopping enabled compared to the chop-off filter profile. Chopping also affects the settling time or the output data rate. Remember, with chop off we have the Sync 4 filter selected and we had an output data rate of 50 samples per second. Because we're continuously swapping the analog inputs with chop on, this means that every conversion needs the complete settling time. Because we have the Sync 4 filter enabled, the output data rate is now reduced by a factor of 4. So it's now been reduced to 50/4 or 12.5 samples per second. The conversion time is now 1/12.5 or 80 milliseconds. Remember, with chop off, the conversion time was 20 milliseconds when continuously converting on a single channel. Note that the settling time for the first conversion has also increased. Remember, with chopping, the ADC must generate 2 settled conversions, average those conversions, and then output the averaged result. So in summary, chopping is good to minimize offset and to minimize offset drift, but it does affect the filter profile and the timing. So in summary, we offer multiple filter options on our parts, and this is good because it offers flexibility. However, each filter has advantages or disadvantages, so trade-offs are needed between the different filter types. Trade-offs in terms of RMS noise, 50-60 Hz rejection, stop band attenuation and settling time.